Howdy everyone. So we're here to talk about the nuclear chemistry chapter. And so it starts off with the story of Wilhelm Conrad Roentgen, who was the first person to really discover X-rays. And basically it was kind of a lab accident. So he had this salt, an ionic compound called barium platinocyanide. So it's barium and platinum and carbon and nitrogen. And it was, he was experimenting with it. And then when he finished for the day, he put it in a drawer in a box and left for the weekend. And when he came back, he opened the drawer and there were some other salts glowing next to, the barium was glowing because it was next to a substance that we found out later emits X-rays. So the word emit is an important one in this chapter. So, a light bulb emits light. That means to give off or produce it. So the barium was producing light from seemingly nothing, which is very strange. A light bulb only produces light if you have it plugged into a light socket. So he was very confused by this and started to investigate. It took a while, but figured out that one of the other metals that was in the drawer had been producing X-rays, which of course are invisible, so there's no way to see them. But eventually this discovery led to the development of the modern X-ray, which of course is used for visualizing bones and other relatively dense tissues inside of a body without having to do exploratory surgery. All right, so just a reminder too that light is a form of energy, just like heat and fire and all these things are. So X-rays turn out to be just a kind of light. It's just a light that we can't see. All right. So this image is called Hand mit Ringen, which means in German hand with ring. And it was the second X-ray ever taken. So you can see here that Wilhelm's bones are visible, and he put the ring on there so he could tell whether we were seeing sort of like a shadow of his bones or whether we were seeing like a reflection, like if you were looking in a mirror. So this is the second X-ray ever taken, and that's what they looked like back then. Of course, now they're much better and a valuable tool in medicine for sure. And then Henri Becquerel discovered that uranium salts can make things glow too, which was interesting because before that, uranium was considered to be kind of a useless thing. It was just a wasteful component that was present in a lot of ore. It wasn't until much later that this energy, this glowing effect that was being transferred from uranium to other stuff was named, and it was named by Marie Curie. She called it radioactivity. And so it's the natural emission, meaning that it just happens in nature. It's sort of an automatic thing. Nothing we can do is going to stop it. So it's a natural emission, like emit, right? So emission means to give off, of energy from the nucleus of an atom. And it is happening around us all the time. All right, so the nucleus of an atom we know has protons and neutrons in it. And so when you have radioactive decay, that means that something in the nucleus is changing about the protons and neutrons composition. So that's interesting. That's different from what we saw in the last chapter, where protons, neutrons, and electrons kind of stay the same in elements all the time. All right. It turns out we really need radiation. The sun, for example, is a giant ball of radiation producing hydrogen gas. And so the radiation that we get from the sun includes, the visible light that you can see that allows us to grow stuff and all these things, but also X-rays, gamma rays, radio waves to a lesser extent. All kinds of light energy is emitted from the sun, most of which we can't see. We call all of that radioactivity. Okay. So Marie Curie was and is still to this day one of the most important female scientists. She was the first woman to get a PhD in science. She was also the first woman to win a Nobel Prize. She won it in chemistry and physics. Still the only person to have 2 Nobel Prizes in 2 different scientific fields. So that's pretty cool. She discovered 2 elements by doing some really time-consuming and detailed work. All right. She died at a relatively young age, about 66 years old, probably because of her exposure to so much radiation. Especially when she was driving a truck that had a mobile X-ray unit on it to try and help soldiers during World War I. The problem then was that we didn't know that X-rays were that bad for you over the long period, so there wasn't any shielding or any way of like protecting the technician. So she was being exposed to it pretty much, constantly for that whole period of time. So she figures out how to isolate these 2 elements from some ore, some rocks out of a mountain. And by doing that, discovered 2 new elements, which is just pretty cool. And from her study of those 2 elements, she developed the understanding of radioactivity, which is just the natural emission of energy from these elements. And it turns out that a lot of elements were radioactive. It's just that those were the first 2 that were studied for their radioactivity. Also, she provided the foundation of Rutherford's work. So Rutherford, again, was the guy who used the gold foil to discover protons and what they are, the sort of characteristics of them. So without Marie Curie's fundamental work on alpha particles and understanding how radioactivity works, Rutherford couldn't have done his experiment to discover protons. And if that were true, we would have no idea now, most likely, of how atoms work, which means our technology would be very limited. Okay, so during the course of studying this radiation, we learned that there's 3 different kinds of radioactive particles that can happen. The first one was actually discovered by Rutherford from Marie Curie's samples, and they're called alpha particles. So I'm going to show you how to write an alpha symbol. This is the typed version. It's a Greek letter, but it looks kind of like a fish. So that's an alpha. Beta is kind of like a bee with a tail that sticks down. And gamma is kind of like an alpha symbol, but like vertical. All right, so alpha particles were discovered by Rutherford, and what's interesting, what he learned, is that if you take a beam of radiation, so this is a radioactive metal of some sort, and it just put it in a lead box because that blocks radiation, and you can put a little hole in it to make a beam. And so if you shoot this beam of radiation past a magnet, so we've got a positive side and a negative side, or an electric field, then it separates into 3 pieces. All right, so the blue one is beta particles. Those were discovered also by Rutherford from uranium. And beta particles turn quite a bit towards the positive end, which means that beta particles must be negatively charged, because if they're negatively charged, they're going to be attracted to the positive side of the electrode here. Alpha particles, on the other hand, turned toward the negative side, so that means they're positively charged. And so Rutherford also noticed something interesting. The beta particles turn a lot faster than the alpha particles do. And so this led him to the conclusion that alpha particles are very light and beta particles are comparatively heavy. Okay, because if you think about this, a heavy vehicle doesn't turn as well. So something like a semi-truck has a harder time turning. You got to make a wider turn. Whereas like a motorcycle can turn really fast. And so that's kind of a similar analogy to what's happening here. Beta particles are very small and light. Alpha particles are really heavy. Okay, as it turns out, alpha particles are just helium atoms, which has the atomic number 2, that are positively charged. So they have a mass of 4, 2 protons and 2 neutrons then, and a positive charge. So that's pretty heavy for a radiation particle. 4 atomic units is pretty heavy. Beta particles turn out to just be electrons. So we usually write electrons with a negative charge. They have no mass, so we write 0 here. And we write -1 down here because in order to form a beta particle, you actually have to destroy a proton. So -1 on the atomic number down here. And then finally we have gamma particles, which were discovered much later by Paul Willard. That's because the gamma particles just travel straight on, which means that they're neutral. They don't have a charge. And it turns out they don't have any mass either. These are just a beam of energy. They're a kind of light, really. Not a particle at all. It's really a kind of energy. So we could even say gamma energy or a gamma beam. Okay. Now, so for these particles to be emitted from the nucleus of these radioactive elements, it means the elements are changing. So like if you give up 2 protons and 2 neutrons, which is a gamma particle, sorry, that's wrong, it's an alpha particle, then your nucleus no longer has those 2 protons and 2 neutrons. So we're changing elements, which we thought at that time was impossible. All right, so imagine how exciting these discoveries were. It was really a revolutionary idea. All right, here's a vocab list. You should know these words. You might think about making some flashcards, right? But we're going to use them a lot. So a reminder of what we know from last